Welcome, everybody. Welcome to this seminar, which is part of the Mechanical Science and Engineering seminar series our department is running here at the University of Illinois at Urbana-Champaign. And today it is a distinct honor and a pleasure, I would say, to present to you Professor Jack Brouwer from the University of California at Irvine with a presentation that has a question mark. Do we really need hydrogen? Well, it is a challenging title, and from knowing Jack over many years, I can tell you that he will be convincing and he will resolve these issues before us in a very rational perhaps the best rational way there is. So a few words about Jack. He is a professor at the Mechanical and Aerospace Engineering at the University of California at Irvine, and where he graduated with a BS and MS degrees, and he got his PhD from MIT. At the same time, he is directing the National Fuel Cell Research Center at the university, and he is also director of the Advanced Power and Energy Program of the university. All these are programs in coordination and partnership with the Department of Energy. Jack is very known for his holistic approach to energy issues. His program involves energy systems dynamics, and it addresses almost all aspects of energy, spanning hydrogen production, hydrogen utilization, hydrogen transport, turbines, wind turbines, solar cells, almost everything in an integrated approach that does also life cycle analysis of almost all energy conversion technologies. Indeed, Jack is a leader. In the past 20 years, he has pioneered testing and experimentation of many aspects of energy. For instance, he is the world's first solid oxide fuel cell gas turbine hybrid system introducer. He is the world's first scientists who use direct DC powering of computer server rack with a hydrogen fuel cell. He developed in the very campus of the University of California at Irvine a tri-generation system. We usually know about the cogeneration systems, but Jack developed a system there that produces fuel, produces heat, produces power. And I can go on and on talking about his awards, his citations, and his publications. Being an educator, he has educated decades of PhD students, MS students on energy engineering. So Jack is an important and influential figure for this big challenge, the energy challenge that the United States and the world are facing on this 21st century. Jack, with no further ado, please, the podium is yours, and we look forward to hearing you going on.
Thank you so much, Petros. I hope that you can see my screen now.
Yes, we do.
Terrific. Well, I really appreciate this opportunity to speak to you today, not only those of you who are at the University of Illinois Urbana-Champaign, not only those of you who are at the Department of Mechanical and Science and Engineering, but also those of you who are in other states and who have other interests. Thank you so much for coming to hear this presentation. So, do we really need hydrogen? It's quite certain we need to move more and more towards these renewable energy technologies that you see on the screen here. But many people wonder if we really need hydrogen. I want to give a brief introduction to the University of California, Irvine. I'm actually proud to have been here for 22 years. You can see the outline of our campus here on the screen. not quite beachfront property, but pretty close to the ocean. And you can see here Newport Beach and Corona del Mar, Laguna Beach, etc. But I'm most proud of the campus and what it's been able to accomplish over its relatively young life. We're the #9 public university in the US, as you can see here, and we're the #1 college in the US, according to Money Magazine, for supporting those who are first-time college participants in their families. And this is a pretty interesting focus of our university recently, which I'm very proud of. But one of the most important things that our campus has done that's directly related to my research interests, I encircle here. Because we have been rated, again, the #1 coolest school in the US for sustainability by Sierra Magazine, the magazine from the Sierra Club. And why were we named that? We were named that because of implementation of sustainable practices on our campus, but also because of our sustainability research. And that brings me to what we have been doing lately here at UCI. We've been doing things that have been reported to Sierra Magazine over this last 11 years. And again, nominated in the top 10 for 10 years in a row and the #1 coolest school this year for sustainability. And what has that included? That's included the kinds of things that we have done. And some of these, Petros, you already mentioned. But in any case, integrated Tiger stations, transmission integrated grid energy resources, an idea that came from our laboratory where we put fuel cells into substations from electricity grid. And people are starting to implement these now. Renewable fuel cell systems that use hydrogen for energy storage, tri-generation systems that produce hydrogen, heat, and power, hybrid fuel cell gas turbine systems, microgrid aspects that include battery energy storage, battery electric vehicle charging, hydrogen fuel cell vehicle charging, and lots of solar. You can see a solar system here that we have installed on our campus, one of over 4 megawatts. A hydrogen fueling station that we have on our campus, integrating fuel cells into trains and locomotives, a focus on solid oxide electrolysis, but including all kinds of electrolysis, the US first power to gas to power system, low emission gas turbine systems and hydrogen use in gas turbines and appliances. Petros mentioned this data center application of fuel cells that we've been fortunate to work on with Microsoft. Power to gas using direct DC solar hydrogen production, and then a fuel cell bus that we operate on campus. Again, only could do it if we have a hydrogen fueling station on our campus and doing this. And these are some of the things that Sierra Magazine, at least, recognized as having us lead in sustainability and being called the #1 cool school. And this was the world's first hybrid system ever built. This was the world's first tri-generation system ever built. This is the most popular hydrogen fueling station in the entire United States. This is a first hydrogen bus in regular operation on any campus in the United States. This was a world first direct DC powering of server rack with hydrogen. This is a first in the US, powered to gas to power. And this is the first in the US generic microgrid controller that controls our whole microgrid for islanding and coming back into connection with the grid. And world use of our low emissions technology in gas turbines. So this is the generic introduction to UCI and to the research that I have been leading together with others here at UCI. And I'm proud of it. So now I want to get into the issue at hand. Do we really need hydrogen? I first want to take us back to a very simple first law analysis of our Earth. If we draw a control volume around Earth, you can see it here. There really aren't too many fluxes that are crossing that control volume. As a matter of fact, solar radiation is the main source that is crossing this control volume boundary. We have some that is reflected back out in the same wavelength spectrum as that associated with solar radiation. And then we have at different wavelengths, Earth that re-radiates energy back out to space. And we could draw an energy balance here. That's very simple here, right? The change in energy on Earth is equal to the energy that is provided by the sun, minus that is reflected, minus that is re-radiated back out to space in a different energy spectrum. And most people think that I'm going to go into climate change and greenhouse gases because they affect this balance, absolutely. But I'm not. I rather want you to think about something else, for the moment at least. And that is to think about our primary energy sources on Earth, which, except for nuclear, all come from the power of the sun. As a matter of fact, the fossil fuels that we use have been naturally produced on Earth from dead plant and animal life, heat and pressure over millions to hundreds of billions of years to produce these fossil fuels, which are precious and high energy density and enable us to, with very little effort, engender incredible things like flight over thousands of miles. But this is such a long time scale that we must draw a hash through this because every other form of primary energy on Earth is so much more quickly replenished. And you think about things like biomass and biogas, things like corn, trees, and grass, which only take months to years for the power of the sun to naturally replenish them on Earth. Or hydropower, again, power of the sun that evaporates the waters, forms clouds, the clouds move over the land, and the clouds rain out water into lakes, and we can use that as a form of energy or energy storage. Wind. Wind is driven also by the power of the sun, creating temperature gradients that lead to pressure gradients that lead to wind forces. And then we have solar power, which the instant you use a unit of it up, another instant comes right back at you. And so you can see that the primary energy on Earth all comes from the sun. So I want to suggest one partial definition of sustainability is to consider requiring conversion of these primary energy resources at the same rate at which they are naturally replenished on Earth without externalities. So I suggest if we started using much, much less of these fossil fuels, okay, it could be sustainable. But this is a very long time scale. Inevitably, we must go to these more quickly replenished forms of primary energy. Because I want you to see what we as humans are doing when it comes to fossil fuel use, at least. This is fossil fuel use in terawatt hours, plotted on a scale that is roughly a scale of human time scale. And what you can see here, this is going from 6,000 BC to 10,000 AD. But if you think about this, our current practices are so obviously not sustainable. Borrowing from future generations, using these precious fossil resources almost as a delta function in the course of human history. It's quite obviously not sustainable. In addition, we have externalities. It's not just that it's not sustainable from an energy conservation perspective, but even though the energy conversion, the things that we've been able to do with energy conversion, which have improved our quality of life, improving our healthcare, improving our transport, giving us freedom of mobility all around the world, these same energy conversion technologies have unfortunately also been the most significant cause of environmental, and geopolitical problems. These are the things I want to call externalities today, although I hope we can get away from that and always consider these things when we look toward energy conversion in the future. One of those, which has been historically a major point of concern and attention from policymakers and the general public, has been criteria pollutant emissions. Most everyone from every political stripe cares about pollution. We don't want it. It's what leads to very serious air quality and health consequences even in the most sophisticated and wealthy of economies. You see this everywhere around the world, even with very strict attention to the pollution and even with all the money you want to spend, okay? I would suggest that policymakers have started to focus a little too much on the next item that you see here, greenhouse gas emissions, and neglected this a bit. We must be concerned about all of these things. The criteria pollutant emissions that give us poor air quality and health and other environmental consequences, but also greenhouse gas emissions. These which lead to climate change. We have additional externalities that many people aren't too concerned about today, but I am, and I think all of us should be. The resource recovery damage that occurs in things like mines, the regional resource depletion, the fossil resources that we depend upon are not equally dispersed among nations or regions. And this leads to geopolitical dependencies and energy environmental justice that is not well served by our current paradigm. And I suggest that the renewable paradigm can be better in this regard. And we have overall primary energy resource depletion, that delta function that I showed earlier. So the good news is that solar and wind power and battery costs have dramatically fallen over recent decades. And this is not by accident. It has been due to some of the policies that have supported their adoption over time and which now have led to their lower cost than other forms of energy in many jurisdictions. And so this is a wonderful thing, something that changes our thinking a little bit, enabling us to think that we can, in the end, get our primary energy from sources that are more rapidly replaced and replenished naturally on Earth. And this has led me and many others, maybe many of you, and the general public to think that we can get 100% of our energy from renewables, especially in power generation. And then if we would just electrify all the end uses and use batteries to handle the intermittency on the grid, and for some end uses, that maybe that's the whole solution. We see our neighbor adopting solar on the roof, or we adopt solar and a battery in our garage and we have a battery electric vehicle. It's starting to look like, hey, if we just all did that, wouldn't that be enough? And then we have, in addition, some people who argue that hydrogen and fuel cells should not be adopted. As a matter of fact, they argue that it shouldn't be because it's mostly made from fossil fuels today, natural gas. They also argue that making hydrogen from water and electricity is less efficient than charging a battery, or that making electricity from hydrogen in a fuel cell is less efficient than a battery, so that the round trip efficiency is lower, and that hydrogen is difficult to store and move around in society. And these arguments are being made by a lot of people and by some people who are extremely influential, like Elon Musk. I highly admire him and most of his practices and businesses, and I hope we have many, many more of them. But I want to suggest that even though I agree with most of this, he and others are being subtly untruthful and not telling the whole story when they argue against hydrogen and fuel cells. And that is because we cannot electrify all end uses. We also can use batteries, and we should use them extensively to handle intermittency on the grid, but they can't handle all the intermittency, only some of it. And not all end uses are amenable to batteries. In addition, round-trip efficiency is greater for a battery unless you want to store energy for a long period of time. Then we can have higher efficiency with hydrogen energy storage. In addition, hydrogen is difficult to store and move around in society, but that's compared to fossil fuels. It's easier than batteries. So, I'd like to go into then a little bit of our research that we have accomplished to see where and how we might best need and use hydrogen to enable this 100% renewable and zero emissions future. This is a simulation of the California grid supplied with 100% renewable energy from wind and solar power in a wind dominant case. Okay, so we've looked at all kinds of different cases, but this is a wind dominant case. And what you see is that the deficits in power occur at certain hours of the year, and these are indicated by the red data that you see here. Okay. And the surpluses of solar and wind power are indicated by the blue power. So this is the residual load, okay, the residual load. Okay, so sometimes some hours of the day and hours of the year, simulating all the way from January 1st to December 31st here, we have a surplus of sun and wind power, and other hours we have a deficit. So all we need to do now is we need to move this around in society. So how do we do that? We have a very large pumped hydro system in California, and this is how large it is. It's about 9 gigawatts if we can have all the pumps turned on at once to pump water from the lower lakes to the upper lakes. And this is why the height of this box is about 9 gigawatts. That's pretty big, but you can see here that would be insufficient to capture all of this sun and wind power surplus from just a power rating perspective. It's also large with regard to energy, stores a lot of energy, almost a month's worth of 9 gigawatts. So we need more. Many have suggested that maybe our battery electric vehicles can be used for grid storage. And I suggest that is a reasonable thing to do. We should dispatch battery electric vehicles to support grid operations. But how much of this storage could it accomplish? If we made all battery electric vehicles into grid energy storage resources alone, in other words, we didn't even use them for driving, all 21 million electric vehicles, okay, if they were 62 kilowatt hours, that's a Nissan Leaf equivalent battery, okay, would only have about 4 hours of storage. It would be at 25 or so gigawatts, okay, but it's a very small amount of total energy. And again, certainly insufficient to move all this energy around, and certainly to move all this energy around on a seasonal basis. The only zero emissions option that I know of that can do something at this scale is hydrogen. And if we only converted existing natural gas storage facilities into hydrogen storage facilities, this is how big that resource would be. It would have nearly 50 gigawatts of equivalent electricity input. If we made renewable hydrogen and pumped that renewable hydrogen into just existing gas storage facilities. And it has almost 2 months of delivering that renewable energy back to the grid. It's the only storage resource that is of sufficient magnitude and capable of doing seasonal energy storage. That is going to be required all around the world to make grid power 100% renewable. Batteries, I suggest, can be used for short duration storage, but aren't sufficient. They aren't big enough for this requirement. We did a similar simulation for the entire world. So instead of just California, we looked at the dynamics of sun and wind power in all the regions of the world, focusing on various continents, as you can see here, and attributing a certain solar and wind contribution to each of these regions. And you can see in Africa, it was mostly solar. Okay, you can see in Asia, it's a 50-50 mix. In Oceania, 50-50 mix. In Europe, mostly wind. Anyways, what we did is we did an annual simulation, again, of all the dynamics of sun and wind power. And we figured out to make it through the year, we would need more than 20 terawatt hours, 20,000 terawatt hours of energy storage. This is a massive amount. And if you ever tried to meet that energy storage with only the very best batteries that we make today, lithium-ion batteries, it would require more than 3,000 megatons of lithium and more than 25,800 megatons of cobalt. From the US Geological Survey, we know that we only have 53 megatons of lithium resources all around the world. Only 25 megatons of cobalt, unless we want to mine the ocean floor, then we have another 120 megatons. But you can see these are orders of magnitude less than we need if we were to make just the first lithium-ion battery to store this amount of renewable energy. In addition, more than 60% of cobalt comes from the Democratic Republic of Congo, not a nation that has good labor practices or good relations with us, by the way. So I want to suggest that lithium and cobalt and these beautiful lithium-ion batteries should be used where they make more sense, in our electronic devices, in cars, and in various applications that require smaller amounts and shorter duration energy storage. In addition, long duration storage is a challenge for traditional battery energy storage systems. This is data that we've obtained from the California Public Utilities Commission, in which utility scale battery energy storage applications were monitored for their performance characteristics. And what we have plotted here is the round trip efficiency of battery energy storage systems, okay, versus their capacity factor. In other words, this is the number of hours that the battery is either being charged or discharged divided by the total number of hours. Okay, so capacity factor. So if you charge a battery and discharge it every day, it has a high capacity factor. If you charge it one day and leave it for a week and then discharge it, it has a low capacity factor. And so what you can see here is that the round trip efficiency for these systems is quite a bit less than we measure in the laboratory. In the laboratory, we do get greater than 90% round trip efficiency for batteries, but in practice here, in utility applications, in large part due to this lower capacity factor, okay, you can see here, these lower capacity factor round trip efficiencies are really low. We get an average round trip efficiency of about 60%. And this is primarily due to self-discharge. There also are ancillary and auxiliary equipment losses that include cooling of the battery energy storage systems, transforming from AC to DC and vice versa, inverting, converting. These sorts of things also contribute to these losses. But I suggest it's primarily self-discharge. That's why when capacity factor gets low, you see round trip efficiency low. So if you want long duration storage, batteries will not be efficient enough. They will always suffer from self-discharge. In the hydrogen energy storage case, you put the energy storage medium in a different facility than the energy conversion devices, the electrolysis and the fuel cell systems. And as a result, you don't have that same self-discharge problem. And to address the efficiency issue, we know that we have future electrolysis and future fuel cell systems that can improve that round trip efficiency. This is data that we have obtained in our own laboratory for proton exchange membrane electrolysis cells. Okay, you can see that in this yellow color here. And then you can see for both electrolysis and co-electrolysis of CO2 and hydrogen to make syngas. Okay, solid oxide electrolysis has a much lower electrical input in kilowatt hours per kilogram that we make. And so there is a potential to also improve the round trip efficiency. However, these systems are not known for their highly dynamic operation, which is something that I've been emphasizing to this point. And I want to spend a little bit of time talking about that as we go forward. We have been able to, with funding from so many different entities and with awesome postdoctoral researchers and graduate students, been able to develop this idea for building dynamic models of all types of fuel cells, electrolyzers, battery energy storage systems. And the key simplification I suggest for enabling us to do these dynamic simulations over long periods of time, like a year, I've been showing you some of these simulations, is to have limited geometric resolution. So this is an example of a planar solid oxide fuel cell with 10 discrete computational nodes. That's an extreme simplification, right? There are all these flow channels and there are all these cells. However, we capture the main physics, chemistry, and electrochemistry by at least resolving the main flow direction of the fuel and oxidant and the changes that occur in the major flow directions. I suggest that if you don't resolve at least this, you cannot get a good model of a fuel cell. The species concentrations and temperatures and local current density change so substantially in this direction, you must resolve at least this one dimension. We are able to also simplify the geometry of even complex can-annular reformer modules and other things, as I'm showing in this discretization below here, right? So this is just 5 nodes. It's a can-annular device. So you have the cylinder in the middle here, you have an annulus here and another annulus here. And so in cylindrical coordinates, we can resolve all of these features, all the heat transfer, all the chemistry, all the mixing that's occurring in this with 5 discrete nodes. I know this is an extreme simplification, but we're trying to do these annual dynamic simulations. And so we can capture most of the physics, chemistry, and electrochemistry with these simplified geometric resolution. And then we can include the dynamic conservation equations. This is an example of some of the conservation equations that we have used historically. You can see this is from a very old publication, but anyways, these are representative where we have species conservation equations, momentum conservation, usually incorporating something simple like a friction factor or so for the flow losses. The Nernst equation for the steady state electrochemical thermodynamics, and then for the dynamics accounting for the electrochemical losses. Again, local losses because they depend upon local species concentrations and temperature, so that we get the major cell voltage, and then you have the species conservation equations too that we resolve. And then heat transfer that's resolved dynamically as well, depending upon the geometry that we are considering. And with these kinds of dynamic conservation equations and simplified geometry, we can simulate these systems dynamically. And this is an example of a full system dynamic simulation for a hybrid fuel cell gas turbine system. So it has a solid oxide fuel cell that you see here. You see the compressor and turbine and generator of a gas turbine system. And essentially all of the heat input comes from the solid oxide fuel cell electrochemical reactions, plus the anode tail gas oxidizer to produce all the compression energy and the generator electricity from the essentially waste heat of the solid oxide fuel cell. And this is showing on the right-hand side that we can dynamically dispatch these kinds of systems to enable load following that follows either a load or that complements sun and wind power. So for example, here we're showing power being stepped down in 2 big steps from 100% full load to 90% full load to 70% full load. And while we're doing that, we're manipulating certain variables like the inlet guide vanes or the current, or the recirculation valve that you can see here, okay, this recirculation valve. So we can manipulate certain variables and control this system so that all of the parameters, and in particular the temperature dynamics that you can see in this bottom plot, can be maintained within the safe limits of operation, okay? So you can see that we have highly dynamic operation with regard to power, and safe temperature dynamics with regard to operating like this, and also surge margin dynamics, right? Because we don't want this compressor to surge while we are dynamically operating it. We can not only simulate solid oxide fuel cells, but also solid oxide electrolysis systems. And these have very interesting thermodynamics that I want to spend just one moment talking about, because one of the reasons that you can get higher electrical efficiency with solid oxide electrolysis is associated just with the simple thermodynamics. So what you can see here is that as you go to higher and higher temperatures, The electrical energy demand, which is given to us by the change in Gibbs free energy, okay, goes down as you go to higher temperatures, okay? Of course, you have then the heat demand that is required, which you can get from other parts of the system, et cetera. So that you end up having lower overall energy that is needed, electrical energy that is needed for making the same amount of hydrogen. But you also have these interesting things that affect the dynamics. In other words, we can operate at thermoneutral voltage, okay? This is often called VTN, okay? The thermoneutral voltage, where there is no heating, no net heating, nor any net cooling required. In other words, what ends up happening then is the overpotential or the electrochemical losses are applied to this heat demand exactly to balance out that heat required for the given current density. And you can see that for a solid oxide fuel cell, this polarization curve shows that point occurring right here, okay? At open circuit voltage though, especially because the solid oxide fuel cell at high temperature has very low activation losses, we can see that we have essentially a straight line that goes through the open circuit voltage here. This is fuel cell operation here, okay? And then this is electrolysis operation. That's the polarization in those two modes. So what you can see here is that there's a region here, a whole region here in which we are operating under endothermic conditions. And as a matter of fact, you can see the degree of endothermicity shown here. And you can see that we have at zero current, of course, the reversible voltage. But as we go to higher and higher currents in solid oxide electrolysis mode, we have more and more endothermicity because we're making more hydrogen. It's at a lower thermodynamic endothermicity, but it's more hydrogen. And that's why it goes to increasing endothermicity. And then of course, after we cross the thermoneutral voltage, we go into an exothermic region. Now, interestingly, most of the existing electrolysis systems, since they have higher activation losses, don't have this dynamic associated with them. They tend to have high electrochemical losses, putting them above the thermoneutral voltage immediately when they go into electrolysis mode. Okay, so with this in mind, let's see if we can actually model solid oxide electrolysis cells and stacks. We've verified that our model can do well against literature data for various temperature conditions. And you can see here our model compared to literature data for different temperatures. And as you would expect, at higher temperatures, you have lower ohmic losses, okay? And as a result, you have a flatter polarization curve. And then I mentioned earlier, our simplified geometric resolution was in a simple 10 node, one-dimensional resolution. Here, this is a two-dimensional resolution of the solid oxide cell and stack. And you can see here that we have 1, 2, 3, 4, 5, 6, 7, 8 by 8, okay, node resolution. And you can see here that we're able to resolve the Nernst voltage, the overpotential losses, the current density, and the operating voltage, okay? We also can resolve, very importantly, the species concentrations, as you're seeing here, and the temperature distribution for all of these systems, and as they are operating dynamically, okay? And then we can put a system around that. We can wrap a system around that solid oxide electrolysis cell, and we can simulate those too, sometimes with spatial resolution, sometimes not. So for example, our ejector and our valve models tend to be not dynamic, but rather simple bulk models. But for the heat exchangers, for the air blower, for all of those systems that might have dynamics that are important, we resolve all of those. And then we can develop control systems to dynamically dispatch these, right? So we have controlled parameters listed here, manipulated variables listed here. And what you can see is that we can control the average stack temperature, the temperature gradient, the hydrogen at the cathode inlet, the steam utilization, and the power demand. And we use various feedback controllers. Sometimes we use cascading controllers, but usually it's pretty simple feedback control or feed-forward feedback control that we are using. And what we can do then is we can show that even these solid oxide electrolysis cell systems can be dispatched to complement sun power, shown in this particular case. And we're showing for a sunny day the dynamics of that solid oxide electrolysis cell. And that's what's shown here. The profile of the sun is shown here in blue. Okay, so you can see that. And you can see here various aspects of the performance. You can see here the system efficiency. Okay, that's in blue here. The voltage efficiency, okay, shown in red, and then the stack efficiency, which very closely follows the voltage efficiency of the cell. Notice that we have actually some endothermic operation. That's how we get these electrical stack efficiencies that are greater than 1. But that we have really interesting crossover points as we're going from endothermic to voltage to thermoneutral voltage to exothermic conditions, okay? And you can see that reflected in how we have to control the system too. So we have an electric heater that we have to dispatch in the beginning here of the day, right? Because we're operating endothermically, we don't have enough power to actually build up the heat within the systems. We have a blower that has to be introduced in the middle of the day for extra cooling because we're operating highly exothermic. And then but we can still do this. Most people think that you couldn't necessarily operate these solid oxide systems in such a highly dynamic fashion, but I'm certain we can. We can even do this for a cloudy day. And that's shown here with the red dynamics that you see here. And you can see here that we have the ability by manipulating these variables to keep that system within safe operating conditions, even during these highly dynamic and crossing over thermoneutral from endothermic to exothermic conditions throughout even a highly dynamic day. We've also been able to show then that you can introduce these kinds of things into microgrids that include all sorts of other energy conversion technologies like gas turbines and steam turbines and battery energy storage and photovoltaics. As a matter of fact, we have all of those implemented on our campus microgrid. And so what we've done is we've simulated what would happen if we added a lot more solar than the 4 megawatts of PV that we have now. And we used a solid oxide electrolysis cell and hydrogen storage system. Some of that hydrogen may be going to our hydrogen fueling station, and others being mixed into the natural gas system to fuel our gas turbine. And we've looked again at annual simulations, okay? So again, this is why we require the simplified geometric resolution to get that annual simulations. And here is an example of the annual electric demand over a year on our campus, and the annual thermal demand that you see on our campus. Okay, as you'd expect, the thermal demand is higher in fall and winter. And then we simulated the case of putting solar almost everywhere we could possibly put it on our campus, and then using power to gas and hydrogen energy storage and hydrogen dispensing at our fueling station to complement that. And what you can see here are the dynamics of 1 week in January. Okay, so you can see this is January 5, 6, 7 through 11. Again, we simulated the whole year. And then you can see the load indicated by this dashed blue line here. This is the load of the campus. And you can see that we have solar power, okay? That's the blue here, some of which goes to meet the demand directly. That's the part underneath the and some of which goes into the electrolyzer, okay? Power to gas, and you can see those here, okay, in the green. But others that has to be curtailed, even in January here, because we still produce too much solar in the very middle of the day. Now, curtailment's not necessarily a bad thing. It's one of the cheapest ways to actually get a higher renewable percentage and just toss a little bit of the renewable energy away. But as we add more and more solar and wind power onto the grid, we're going to be increasingly forced to store that renewable electricity. And then if you look at, for that same week, we have the thermal demand. And the thermal demands can be met by the steam turbine taking on the electric power generation. That's what's shown in yellow here. But we also have that heat being used in this gray here, coming from the gas turbine that is partially fueled now, right, with the renewable hydrogen that we made on our campus, okay? We still have some excess thermal that we see here, okay? That comes typically in the middle of the day, again, when we have all that excess solar and the heat that comes from the gas turbine combined cycle plant. Okay, we've applied it not only to our own campus, but also to other Midwestern, for example, situations. So this is one in Texas, okay? We did this quite a long time ago, but this is for a case in which we measured the dynamics of Texas wind farm and the adjacent, and that's shown here in the green for 1 week in October. And you can see here the dynamics of wind, okay? And then we had the adjacent town or city demand dynamics in magenta, as you can see here. And whenever we had excess wind, we would make hydrogen in an electrolyzer, and that's shown here in the blue. And we would place that hydrogen into an adjacent salt cavern. This was at the time, 2010 to 2013 timeframe, being considered for hydrogen storage. So we thought it might be reasonable, especially since Texas has more than 3,000 salt caverns. What you can see here is that we can take that hydrogen back out of the salt cavern, put it through a fuel cell to meet the power demand when wind is at a deficit. And what you can see here is the week-long October simulation of the pressure dynamics in the salt cavern and the temperature dynamics in the salt cavern, which are maintained between the maximum and minimum pressures. And you can see for the whole year, we are able to actually not only accomplish hour by hour, day by day, week by week, but also seasonal storage of that wind energy. You can see here, the pressure is slowly building up on average in November, December, January, February, and March, but then is mostly given back to the community in July, August, and September. Now, when we did this, there were no operating hydrogen storage salt caverns, but now there are 2 that are currently in operation in Texas, and they're proving that this is a safe and very effective way to store renewable hydrogen. But what if we don't have a salt cavern? Well, in California, we don't have one. But I suggest that we could use the natural gas system, another underground storage resource that could not only provide that storage, but also deliver that renewable energy content. And it can do so with very high reliability. The Gas Technology Institute, very close by to UIUC, well, Chicago is pretty nearby. They've estimated that 99.999% available gas delivery to customers. And this makes it a very interesting resource for using for our renewable energy future. It would provide, just in Southern California, 13 terawatt hours of equivalent electricity storage. That's $2.6 trillion value with regard to DOE future battery costs. Even if we just put 5% hydrogen into the natural gas system, it would be $130 billion at future battery costs. Now, these numbers are so big, I want to relate them to something that maybe we understand a little bit better. How about UC Irvine tuition and fees? We could send the entire population of Orange County, every man, woman, and child, to 4 years at UCI for only $39 billion. We could make all University of California schools, 4 years of the entire UC population would only cost $4.7 billion. The interest alone off of this value of this massive energy storage system could make all UC schools free forever. We got to realize how big this resource is and why it will be then so valuable to our energy future. And it's been proven resilient under all sorts of circumstances, in blackouts, in winter storms, in hurricanes, earthquakes, Japanese super typhoons, the Napa fire, all kinds of fuel cells and gas delivery underground circumstances. And it's such a massive resource. I wanted to have this idea in your head. I want you to think about this, because we could first mix up to a certain percentage into this system. And this is not such a great thing with regard to decarbonization itself in the gas system, because we can only go up to 5 to 20%. The biggest reason we want to do this is so that we can add more renewables to the electric grid. That's why we want to do it at a certain percentage. And then I think we got to piecewise convert it to pure hydrogen or a renewable hydrogen derivative. And so I asked one of my PhD students to think about, hey, what if we put solar in the desert here and we didn't build any transmission lines? We just wanted to use the gas system to move that energy. And this is 20 miles by 20 miles here. That's that area that you see here. If we built just this one project and we closed the valves here to the fossil and we put just renewable hydrogen into these pipelines, how big would that be, and could it manage it? Well, those 4 pipelines that go through there can definitely manage the dynamics of the hydrogen production. It's below this green line, which is the maximum pressure for all 4 of these pipelines. We even have a little bit of excess capacity. And just this one project could produce 40% of all of our electricity. 40% of all of our electricity. And it does the transmission and distribution for us as well. This is pretty remarkable to think about this, right? One 20 by 20 mile square project, and just using the gas system for hydrogen takes California from its current 35% renewable to 75% renewable. I want to kind of end pretty soon here with why we, I think, need hydrogen. And I want to suggest I'm not the only person that knows this. I was very fortunate to work with a whole group of amazing scientists and engineers led by my very close colleague, Steve Davis here, to investigate the completely zero emissions energy systems of the future. And you can see there's a lot of things that are going to be required, not just electrification and batteries and sun and wind power. You can see that we have chemicals and hydrogen, and we need to have something to make ammonia and to fly and to make cement and steel and reliable electricity. And these kinds of things are increasingly being recognized as possibly requiring hydrogen for achieving completely zero emissions. And I think especially in the transport sectors, there are some things like I'm showing on this screen, anything that requires rapid fueling or long range or large payload is going to need a zero emissions fuel. And batteries don't do well in these circumstances. Hydrogen and its derivatives may. Hydrogen is also required for industry. Many applications for heat or feedstock cannot be electrified. And you look at things like steel making or cement production, plastics, ammonia and fertilizer production, computer chip manufacturing, pharmaceuticals, and other things will require something like hydrogen and its derivatives to make them zero emissions. Okay, and I'm going to end with just 2 Gedanken experiments very quickly. That is, thought experiments after Einstein's naming of such. You got to just think about something that you'd like to have happen in the future and then do some high-level analysis of that. And one of those analyses that I'd like you to think about is, can we ever make the LA Long Beach port complex completely zero emissions? And there are 2 technologies that people are suggesting for this purpose. One of them is battery energy storage systems. You see these in the red data on this plot. The other is hydrogen, and I'm showing gaseous in green and liquid hydrogen options in blue. And what I'm showing here is the percentage of original cargo space and net tonnage on ships of various sizes. TEU refers to the 20-foot equivalent units. That's kind of a container size that is typically used for the size class of ships. And what you can see here, it's pretty obvious that hydrogen options can, especially the liquid hydrogen options, almost retain 100% of the tonnage and volume. Whereas battery electric energy storage systems, okay, at the best can only support 40% of the original volume and only about 8% in only the smallest size classes of these ships. Of course, with gaseous hydrogen storage, we lose almost 20% of the volume here because that takes up a lot of volume in comparison to diesel. And we know that these hydrogen options can go long distances. So you can see here, 17,000 nautical miles, and they still can carry between 100% and 90% of the original cargo, but the battery energy storage systems can't make it over these distances. And then we wonder, can we make all that hydrogen? So we've looked at various options for making all this hydrogen, and we simulated just three offshore wind platforms. And just with those 3 offshore wind platforms, we can make 8.9 million tons per year of this renewable hydrogen. And this would enable us to decarbonize all the ships going into the port, all the trucks going into the port, and all the trains going in and out of the port, and to electrify the short range options. Just wind power in 3 large wind farms can make the entire port complex of LA Long Beach zero emissions. How about another Gedanken experiment? We've been fortunate to work with Microsoft over many years to think about how we can make data centers zero emissions. And we've simulated those cases of battery energy storage, power to gas, that is complementing the solar and wind, or even cases that makes hydrogen out of all the renewable power and uses fuel cells directly to power all of the servers. And we've looked at many different locations. We've simulated the modules that you see here and the wind power that you see here. Notice that we have lower round trip efficiency that we're assuming for the electrolyzers, and we're assuming liquid storage, which uses a lot of energy to store the hydrogen. And we're accounting for self-discharge and round trip efficiency for the battery energy storage systems too. And we can optimize this for various things. We can optimize it for the most data going directly to the data center. We can get 81%. That's pretty good. That's pretty good. If we have a 50-50 mix of wind and solar, we could also minimize the storage amount that is required. That would require more solar and less wind. We can have the lowest energy capacity installed. That would require mostly wind in this particular Wyoming location. We've also done techno-economic analysis of these cases, and every single case that we have simulated so far, even accounting for all the costs of liquefaction and storage and boil-off losses and everything, has led to a substantially lower cost of energy going to the data center in a hydrogen storage case compared to a battery energy storage case. And this is primarily because we require seasonal storage to make it reliable for the whole year. And that leads to just a huge battery cost, even though we can install less solar and wind because it's more efficient. Every case is cheaper in the hydrogen case. Now, I haven't been able to discuss every single aspect of hydrogen that I think makes it essential for sustainability, but we wrote a paper on this. This was published in the journal Current Opinion in Electrochemistry a couple years ago. I hope you get a chance to look at that afterwards and see if you have anything that you want to argue with me about. I'd be happy to discuss that. So in summary, we must and we will inevitably increasingly depend upon solar power and its more direct derivatives to engender air quality, greenhouse gas emissions and climate, energy, environment, and geopolitical sustainability. It will also help us, if we're careful, to address environmental justice. However, the dynamics of such a future are challenging. They are going to require complementary dispatch and massive storage and seasonal storage. And for that, we need all of these technologies, okay? We need all of these technologies, batteries, hydro, power to gas, hydrogen energy storage. This is very important for engendering our zero emissions future. And I want to suggest that the one that has been ignored the most up to this point, but is increasingly garnering attention, is power to gas, and hydrogen energy storage. I think they're going to be indispensable to our zero emissions future because of some of the features that I hope I've been able to convince you of today. So, do we really need hydrogen? I suggest absolutely. I don't think we can get to zero without it. So thank you so much, and want to acknowledge a whole bunch of colleagues, funding, and intellectual contributions from graduate students and postdocs that contributed to most of the stuff that you saw here. Thank you very much.
Thank you very much, Jag, for this informative and very insightful presentation of this holistic approach to net zero. Thank you very much. Yes, so now we will open the floor for discussion. We will have the panelists who can start raising questions, making comments, and at the same time, those who would like from the participants, those who like to ask questions, please type them on the chat, and Jack will be very willing to answer any questions you may have. So I've already seen some questions that are coming, Jack. Perhaps you can start questions while the panelists that we have may start coming up with their comments and their questions as well.
Yes, I'm starting to see some comments and questions in the chat. I stopped sharing, but I can possibly reshare if I need to going forward. I'm going to just start by the first comment here. Musk says fuel cells. We say bad, B-A-D, batteries. Cute. I like it very much. Thank you for that. He cries round trip efficiency, but we say resources and recycling. Yeah, I hopefully touched upon those topics. Appreciate that comment. How about long distance transporting of gaseous hydrogen via unmanned drone airships? This is very interesting. Of course, you know that hydrogen is quite interesting for its lightweight. And of course, it was used quite often until the Hindenburg disaster. Again, hydrogen did not cause that disaster. As a matter of fact, it might be attributed for saving lives in that incident. But yes, I think that's a really interesting way to transport it. And it's a very efficient way of transporting it if you don't already have existing, let's say, underground pipelines and the like. Wow, I'm getting so many questions here. Please address green hydrogen via biomass. This is really interesting. Yes. And we absolutely must use our biomass and other waste streams in a way that we convert them for a useful energy purpose. We're forever going to have these streams with us. And some people don't like things like gasification because it could lead to criteria pollutant emissions, although that is increasingly, we are increasingly able to minimize that. Some people don't like even making renewable methane using anaerobic digestion because the methane itself is a potent greenhouse gas and sometimes that leaks and things like this. But again, these are things that we can mitigate. We're going to always have the anaerobic digestion with us. We're going to always have these biomass resources with us. We're always going to have these waste streams with us, and we absolutely must manage them. And one of the vectors that might be important for managing them is to convert them to hydrogen. And if we can convert those to hydrogen and sequester the CO2 at the same time, we can engender negative emissions even. So this is really interesting. The sun energy comes, it makes the biomass, it makes the biogas resources. Consuming CO2 out of the atmosphere. And then if we can sequester it and make hydrogen out of it, that's a really interesting way to make renewable hydrogen that we must engender in the future. I want to suggest that I'm an advocate for that, and we've done research on that. But the focus of my presentation today was intentionally upon the renewable production via electrolysis of sun, wind, and geothermal, other renewable electricity, sources. Why did I emphasize those? I emphasize those because around the world, in comparison to our energy demands, those will be by far the largest contributors to our hydrogen economy, the portions of the economy that hydrogen must manage. That's available to a greater extent than the biogas resources, and it's a larger amount that can be contributed in our zero emissions future. So please understand, this is batteries are great. We're gonna have to use a lot of them. Bioenergy is great. We're gonna have to use a lot of it. I think hydrogen is just gonna be a little bit bigger in its magnitude of contribution in that zero emission future. Could you comment more on the 2 Texas salt cavern projects? Yeah, both Air Liquide and Praxair have an operating salt cavern. Let me explain that a little bit, what a salt cavern is. This is due to hydrologic, mining of geologic resources, which are salt domes. Okay, so salt ends up being accumulating under some in some geological formations under Earth, okay, and above Earth, okay, in these formations that are large deposits of almost pure salts, okay? And if you want to use hydrologic mining, what you can do is you can just drill a hole through the earth and get into the salt space, and then you pump water down there. Of course, the salts will dissolve in the water, and then you pump the water back out, and then you evaporate the water to harvest the salt. And this has been done for hundreds of years, I think, a long time, certainly, in places like Texas and Europe. There's a similar complex in Utah, okay, many different places around the world. And these have been used after their useful life as a mine of salt for various forms of storage. As a matter of fact, liquid petroleum, distillate fuels, and other things have been stored in these. And people didn't think necessarily about storing hydrogen in those. They didn't know for sure if they would be leak-free. They didn't know for sure if there might be other like reactions between the salts and hydrogen or so that might be concerning. But since 2016 or so, there have been European salt caverns and 2 salt caverns in Texas that have been in operation. And Air Liquide tells me that they can't even measure the leakage from their facilities. They know how much they're measuring going in, how much they're measuring going out, what the pressure is in there, and it looks like it's negligible leakage, which is really amazing, okay? So that's a little more information. I don't know if that's sufficient for answering that question. Okay. Someone's asking about the water availability for hydrogen generation. Yes, we've looked at that, and there are several other people, researchers around the world that have looked at this. We know that the amount of water that is required for the paradigm that we are looking at, for example, the amount that we are looking at, the water amount for the paradigm we are considering, which will require hydrogen for meeting about 20% of all energy demand, okay? That's about it, okay? We're gonna use direct solar and wind, we're gonna use batteries, we're gonna use everything, but this 20% of all energy demand probably gonna go through the hydrogen vector. The water will be a small amount of the water that we already move around in society and, quote, consume. What do I mean by that? There's a couple of analyses that we have performed ourselves and a couple that others have performed. On an individual residence basis, it means that we need about 1.6 gallons per day. This is just one toilet flush. Okay, that's one point of comparison. Another anecdotal comparison is associated with the whole of Southern California. If we would make the whole of Southern California all hydrogen fuel cell vehicles and powered them all by electrolysis of water, okay, hydrogen that's made by electrolysis of water, we would use less than 1% of just the water that goes to Southern California from Northern California in the California aqueduct. Okay, and that's a very small fraction of the water that we use already today here in Southern California or in Northern California, especially for agriculture. So if you look at this, I don't think water is going to be a problem. However, it's of concern, especially because it's not always available where you want it. So for example, that solar farm that I imagined and that we simulated in the desert, that one we might have to think about how we would deliver water to it. Could we take it from the Colorado River? That might be important, okay, to consider. Okay, so this is a very good question. I want to suggest, though, that around the world, we already move way more water around than we need for this purpose. Okay. What are the main materials challenges for use of hydrogen in the ways that you have outlined? This is a question that I want Petros to answer. However, I want to suggest that hydrogen embrittlement is one of the most important considerations in steel and pipeline steels. Petros is an expert in this, a world-renowned expert in this, and he and I have worked together in the past on this a little bit. And this remains something that I think is an active area of research and a required area of research if the vision that I presented is to be engendered. There are other things too, though, that are associated with valve gaskets and seals. There even are weld issues that might be different from the original pipeline steel materials that should be addressed. There also are things associated with the leakage rates. Okay, that's not quite a materials challenge. It's more so of material morphology, and if we have through leaks, okay, it's going to leak quite a bit differently. There might also be some challenges with regard to plastic materials. However, the research that I see coming out of Europe especially is suggesting that most of the plastics that are being used nowadays in the distribution systems in Europe and in the United States are going to be able to handle hydrogen just like it handles natural gas today. That may not be a full summary of the considerations, but there definitely are materials challenges. Petros, do you want to add to that?
No, I think that Jack, you gave a very, I think, complete answer. I would say the only thing that I would add would be that this is an old problem, and right now we know how to tame it. We have the capabilities, we have the tools, many new tools, characterization, experimentation, etc. And we need how to tame it. It is like the internal combustion engine. If you don't change the oil, it is going to fail, right? But you do maintenance, you know, after a certain amount of miles or a certain amount of time, you have to go and change the oil, and you can keep the engine going for 100,000 miles, 200,000 miles, and so on and so forth. So yes, indeed, it is a materials problem, but we know how to tame it.
Very nice. I was going to say that at least the initial research that I know we did together suggests it's a manageable problem. That's my overall assessment of it. So thank you for those additional comments. So there's a question here about the useful life of proton exchange membrane fuel cells and degradation over time. This is a nice question. These fuel cells were known and have been known to perform very well, and as a result are already available in commercially available, although limited production vehicles from Toyota and Honda and Hyundai and others. These fuel cells are lasting long enough that they can go 100 to 200,000 miles, okay? But they have a platinum loading that is leading to this long duration performance, okay, that must be lowered in order for them to be cost effective and last long enough. Okay, so there's a trade-off there, right? If you put enough platinum in, they can last long enough, and there's lots of research and development over a couple of decades at least that is contributing to all of the mechanisms of degradation. There's tons of mechanisms of degradation that have been studied, but in particular, there's also system level changes that have been made to not let it sit at open circuit voltage for very long, to make sure that you don't have any kind of oxygen that gets into the anode compartment that can lead to carbon corrosion and things like this. Okay, so there's a whole bunch of degradation mechanisms. I won't go into the details of that. But the key thing is that we can make fuel cells last long enough. The proton exchange membrane fuel cells can last long enough. The solid oxide fuel cells can last long enough. But the cost-effective engendering of that is still an issue. Okay, and this is especially the case if we want to engender heavy duty. Okay, and this is an active area of research here at UCI, especially from my colleague Irina Zenyuk. If we want to make it last 300 to 500,000 miles, then you have an additional challenge. Now you can pay a little bit more for, a heavy duty engine. You're using it a lot more. If you want it to go 1,000,000 miles, okay, that's the kind of thing that we're aiming for, and that is still an active area of research. Hopefully I gave you a little bit of insight into that. That's a nice question. Okay, next. Any commentary on different types of electrolysis, alkaline versus PEM versus alkaline exchange membrane, and solid oxide, which is the main one that I talked about? Yes. Alkaline and PEM electrolysis are, as most people know here, these are the ones that you can commercially buy today. And as a matter of fact, they are starting to come down in cost very substantially because of large orders that are being made, not necessarily here in the US, but internationally, which is a really awesome thing to see. It could engender this idea of making hydrogen at a very low cost as we introduce more and more renewables over time. And alkaline fuel cells are the least expensive options from what I've been able to see. Proton exchange membrane electrolysis systems are a little more expensive in most of the commercial bids that I've seen. But proton exchange membrane electrolysis has some advantages with regard to its ability to produce higher pressures by electrochemical compression, okay, and ability to sustain a differential pressure, if you'd like, between the hydrogen side and the oxygen side that alkaline can't engender. I think also you would find that proton exchange membrane electrolysis systems might be able to handle higher dynamic performance characteristics out of the gate. I think both of these could do dynamic operation. So they have various features that make them both desirable. The alkaline exchange membranes, these are still under development. I don't know of a commercial system that's available there. Neither do I know of a solid oxide electrolysis system that's commercially available today, but they both also have advantages. And with regard to alkaline exchange membranes, they avoid some of the challenges that PEMs have. And then you have with regard to, and in particular, the ORR, the oxygen reduction reaction. So you have lower polarization losses associated with the oxygen reduction reaction. But in solid oxide, also you have very much lower losses and the ability to use heat. And I hopefully described that a little bit in the presentation, that you can have very low electric input and a little bit of heat input, and you can have super low or even above 100% electric to hydrogen conversion efficiency. Okay, now again, that you have to give heat to the system to do that, okay? So hopefully that's a little bit about all the different electrolysis technologies to answer that question.
Jack, may I ask a question?
Sure.
On behalf of my dean here? Yes.
Great.
What is the biggest impediment to realizing hydrogen economy? How much is it policy, political will, or more technological barriers? Can you comment on the role of nuclear in hydrogen? So
those are great questions. I want to suggest that I think it's an equal measure of political will, which must be engendered by first a general public understanding of what we're up against with regard to the pollutant emissions, the greenhouse gas emissions, and trying to engender the policy frameworks that we already have as law in many jurisdictions. So for example, California is going to be decarbonized by 2045. So is New York, so is New Jersey, so is Connecticut. Okay, so all these jurisdictions, they're already committed by law to do this. And if you don't realize that we need all of these things, but we need the solar, the wind, the geothermal, we need the nuclear, okay? and batteries and hydrogen, then we're not going to make good policies. But people are starting to come around to realize that we need this. Okay, so there's a very big aspect that is policy requiring. And this is the same way that sun and wind power became cheap. We established reasonable policies for subsidizing their use originally, and then forcing the utilities to buy them secondly, and now they're the cheapest. Okay, so we need good policies. But there are technological things too that we still have to advance. And these include some of the hydrogen topics that we've just mentioned, right? We don't know yet if we're going to engender an easy transformation of these pipelines to carry renewable hydrogen. We have some research and development topics associated with the compressors and the valves and the regulators. We have some issues with regard to the various storage facilities that we have around the world. We don't always have a salt cavern. Salt cavern's proven for hydrogen, but the other ones aren't. Okay, so there's a whole bunch of research and development questions still that we must resolve to engender the kinds of characteristics that we are talking about. Let me mention a couple more things about nuclear, because you asked that particular. We did a little bit of research on this. I have only one PhD student so far that's looked at this, but I think it's going to be very important for nuclear facilities in a highly renewable world to become dynamic in their dispatch. And hydrogen is one of those vectors that could enable that. And what we looked at in this one PhD dissertation is the possibility of using the nuclear reactions to heat up a salt, okay, and then to have that salt flow through a gas turbine power plant for the production of electricity during the times in which the sun wasn't shining, the wind isn't blowing, but then also couple that with a high temperature electrolysis cell, which would use that same heat input, okay, and any electric input that you wanted from the gas turbine to essentially make it a 200% dispatchable device. We could actually have the solid oxide fuel cell take electricity off the grid, okay, a 200% dispatchable nuclear plant, okay? And this was what we've simulated. We still have that publication, not submitted yet for publication. So I could share the dissertation though that looks at that. So yes, nuclear has to be, I think, part of the solution, but I suggest that if we can make them dynamic, dispatchable, it's going to help with regard to their adoption. And hydrogen can help with that.
Thank you, Zach. Thank you very much. Yeah.
Did you have another question that you wanted to point me to?
I will, as you try. I'm searching through the questions as well.
Okay.
If any of the panelists would like to ask any question, please, or make a comment.
Are they? Are we allowed to let them in?
Yeah, I think.
Okay, good.
Yes.
It would be nice to see some of them, see some of you.
Julia, is it possible to see the panelists here? I see Kyle, for instance, my colleague Kyle. Kyle, go ahead in case you want to make a comment.
Sure. Unfortunately, I can't share my video, so I'll just speak. Nice to meet you, Jack. I really
Nice to meet you.
enjoyed your talk. And from what I understand, most of the focus of your analysis and the research that you've done is using existing electrochemical components. Those may be, not be commercialized yet, but they're existing. I'm curious to hear your perspective on what opportunities you see for the future innovation of electrolyzers and fuel cells. I know you touched on that to some degree, but maybe you can answer the following question. What do you think are the most important questions to explore in that regard from a research standpoint?
Well, I'll mention a couple of things. Lithium-ion batteries have had a very significant investment, and they're one of the most wonderful inventions of our recent history. Thus, the Nobel Prize for such just recently, right? But I want to suggest that we have an opportunity for more earth-abundant batteries that might have different chemistries, and even better recyclability that could be engendered by alternative chemistries. Even, for example, considering lead acid again. Because I think the recycling of that is a very important aspect with regard to batteries and also earth abundance. So, asking some questions about that, trying to find battery chemistries that might work better. On the electrolysis side, I think okay, I mentioned before, we have proton exchange membrane and alkaline systems that exist, and these are already coming down the cost curve.
Right.
I think that there's not like a huge set of research questions that are associated with those. However, continuing to bring them down the cost curve will have some research and development topics that I don't want to enumerate. I think that the companies will identify researchers that they want to work with to address some of those things. Alkaline exchange membranes, these are still emerging, and so are solid oxide cells, still emerging as technologies that may contribute to our future. And again, alkaline exchange membranes less susceptible to some of the poisoning and have lower polarization losses, and so could be useful for that purpose. And there's a lot of research questions that could be addressed with regard to those. And same with solid oxide. One of the biggest ones for solid oxide was that people don't think they can be operated dynamically, okay? Because if you buy a solid oxide fuel cell system today, it's not operated dynamically. They don't let you operate it dynamically. It has to be moved very, very slowly. Okay, this is why that's one of my research interests, is I think that that's a big deal. But there are other things too, like degradation. And degradation mechanisms, someone pointed out earlier also with regard to proton exchange membrane and alkaline. In electrolysis mode, that's not so big of a challenge, but in fuel cell mode, the degradation can quite readily occur under certain conditions. Catalyst loading reduction in proton exchange membrane is still a very big research topic. I think that's going to have to occur over time if we're going to use these to the extent that I've suggested we do in my presentation. I don't know if I put enough on the table there for you.
No, I appreciate that. I think with the breadth of work that you've done, it's really helpful just to hear your thoughts about this, where you see the opportunities. Of course, everybody has their own opinions about where the opportunities are, and some of whom are more poised than others to actually address those questions. I'll let someone else go. I have another question I'll follow up with in a bit.
Okay.
Is my colleague Jim Stubbins around? Jim, are you around? That's okay.
I didn't see Jim in the attendees, Petros.
Okay. All right. Jack, we've got a question here. I recently read about an Australian company creating residential hydrogen batteries to pair with your rooftop solar system for only about $25K. Do you anticipate any significant safety or regulatory barriers for using a system like this in the USA?
Okay, so first of all, that was a very exciting announcement. I noticed it too. And interestingly, we started doing research on that back in 2000. I think that this is quite interesting under certain circumstances, and in particular, when residential neighborhoods might be, when we have residential neighborhoods that are new, okay, and not directly adjacent to existing infrastructure for gas and electricity. I don't see it as being ubiquitous, in particular with regard to already urban environments that already have a connection to the electric grid and to the gas grid. And I say this primarily because I think it's going to be way cheaper and have less risk to engender the same zero emissions characteristics and long duration storage that this Australian company is trying to engender at an individual residence by use of the larger grid infrastructure, both on the gas side and the electric side. And if you think about it, trying to put one of these complex systems at individual residences where you don't have an energy expert, you don't have someone that's going to come and fix it automatically, and these kinds of things, and the cost per unit of energy storage that you get, because every single installation requires a salesperson, an inspector, all of these things. I think it's going to be very difficult to make that the most important way that we do hydrogen energy storage. It's pretty exciting, though, to see that. And under certain circumstances, like in remote situations, in places where they're building new places to live, where they don't have ready access to the electric or gas grids. Yeah, I think it's a really cool idea, You asked if there are significant regulatory and safety barriers. Absolutely. Every time we've done a hydrogen project, we've had to educate and discuss things with the local jurisdictions, the fire marshals, the city planners, and the like. Eventually, though, I think it's going to come around, and people are going to realize hydrogen is different, but that with understanding of the differences, it can be handled at least as safely as we are handling current infrastructure fuels, which we accept readily. We readily accept gasoline. We readily accept natural gas coming into our homes, into our garages. And again, it's very different, must understand those differences, must have adequate engineering and precautions for that. But it's going to come around, I think, when people begin to realize that.
Jack, I see that we've almost, you almost answer the majority of the
questions. Almost every question that's here.
I've got a more general question, I would say. It has to do with economics and the politics, how the economy is going to go, right? As you know, now we have a new administration in our country here, right? And the climate change is associated with job creation, right? And as you know, a big sector of the economy is the oil and gas industry. Yeah. What is the role of the oil and gas industry here, especially with respect to the green hydrogen and blue hydrogen? Because when we talk about transition to carbon neutrality, let's say by 2050, I mean, we cannot get green hydrogen from beginning tomorrow, right? There's going to be the blue hydrogen that can play a big role. And how does this relate with the economics, for instance, of this big industrial sector of the economy?
Yeah. Maybe some of the people online don't know what green hydrogen and blue hydrogen are. So I know you know this, Petros, but I'm just going to reiterate that quickly. So green hydrogen is the hydrogen that I've been mostly talking about, which is coming from renewable sources, including biomass and biogas, okay, but also renewable electricity electrolysis of water. Okay, so this is green, okay. But blue hydrogen, which is kind of the next best color, if you will, could be made from a fossil fuel like natural gas with carbon sequestration, which has similar benefits when it comes to climate. Okay. But some people do not like blue hydrogen as much as green hydrogen, and that's also for good reason. I presented that delta function for this purpose, right? Yeah, we can use it for a while, but we can't use it forever, okay? But I think that this while is very important from what you said, Petros, okay? This while is important for engaging those who work in these industries immediately and for engendering some of the characteristics that we need to evaluate and to do research on in the immediate short term, because we can make hydrogen super cheap in this way. As a matter of fact, the 2 caverns that are in operation down in Texas are not storing renewable hydrogen. They're storing hydrogen that is not even blue. It's gray. It's made without sequestration of the CO2 from natural gas, okay? It's not quite black. All these colors are pretty funny. But anyways, So it is important for us to, in the short term, establish this hydrogen infrastructure and to do the research and development and demonstration of various aspects of the transition that we need, and engage the corporations that have the workforce, that have the invested infrastructure, and can contribute to this zero emissions future. But if we don't give them a pathway, they'll fight us. Also, politically, it'll be a problem. So I think that both technically and politically, we got to work together to reach this future. And that's the only way I think that in the end, we're going to make this transition economic and fall down the cost curve, and include the labor forces of all of these entities as well. Those who claim that we can replace pipe fitting jobs with electric working jobs will have a more difficult mountain to climb. Okay, that's all I'm saying. Okay. And then if you look at the other characteristics that the grid, electric grid plus gas grid can provide, like the additional resilience and the massive energy storage and all these kinds of things, I think it starts to make a lot of sense that we support both of those techno-economic paths, right? And involving both the fossil gasoline and gas industries together with electric industries.
Thank you very much, Jack. Thank you. Do you have any more questions or comments from the panelists?
Someone did ask a question about 3,000 plus salt caverns in Texas, but none in California. So in California right now, we have depleted oil and gas fields that we are using for natural gas storage. These are currently being, in very limited circumstances, evaluated for small amounts of hydrogen mixed with natural gas in Europe, which has some similar facilities. Around the rest of the country, we have some of these similar. Okay, so like throughout the Midwest, I think especially like, Oklahoma and the panhandle of Texas, there's lots of depleted oil and gas fields. Up in the north, like Alberta, Canada, and going down into North Dakota and things like this, you have these other facilities there. All throughout Pennsylvania, Ohio, and wherever you have coal, you have underground facilities. Coal and or oil, you have underground facilities that might be able to be used. So we have dispersed throughout the United States other types of underground storage facilities that could possibly be used, again, with some research and development investment. So that's what I think it looks like around the rest of the country. And Kyle, you unmuted yourself, so maybe you have another question too. You said
Let me ask a more technical, detailed question. Because my group also does a lot of electrochemical modeling, so I can appreciate some of the aspects of your work there. And it's nice to see how you fitted the different subsystems together. So I guess I actually have two questions. The first of which, relates to the dynamic nature of the models that you develop. And in almost every kind of electrochemical device that my group works with, and I imagine with the electrolyzers and fuel cells that you work with, you have porous electrodes. Mm-hmm. So when you show the picture of the sort of coarse-grained control volumes that you use to discretize the system, that's one scale of the discretization. But then there are certain other kinds of assumptions that may not actually be consistent with the dynamic behavior of the materials at the pore scale. For instance, the film law of mass transfer, right? Especially in a dynamic context, usually that the mass transfer coefficient is determined from a steady kind of simulation where you only have one frequency component. And so I'm wondering, what have you seen, when you've attempted to validate the models that you've worked with, do you see a good match across the frequency spectrum, or where do you see opportunities for improvement in that regard?
This is a wonderful question that we have only just begun to start looking at. So for example, trying to couple measurements using electrochemical impedance spectroscopy, especially in the mass limited regime, mass transport limited regime, to see if we might be able to, through understanding how the gases are moving through the pores. We don't have in our particular circumstances, we don't have two-phase flow, so it doesn't get that complicated, but it still gets complicated. Yeah. With regard to the Knudsen diffusion regime and other continuum regimes. So we're just starting to look at things like this. I think that for the most part, we have tended to simulate these systems where they are not in anything close to the mass transport limited regime. And so we don't run into these kinds of circumstances that often. And as a result, we've also been able to validate our models versus data, even operated dynamically, under a lot of different circumstances. But it becomes a lot more complicated if you end up in a proton exchange membrane fuel cell or electrolysis, where you end up having two-phase flow, for example. And it also becomes more complicated when you're operating in these high current density regimes where you could have mass transport limitations. Absolutely, we wouldn't be starting to do some research in this area if we didn't think that was important.
Right. Yeah. And I think, if these kind of devices are really going to serve as solutions to the different types of grid management functions
yes,
that, it's thought are needed. There's a whole range of frequencies that we could see. You've touched on an important point, though. It's not just about the frequency of it. Well, what's the magnitude of the current? What regime of the cycling are you really in? What's the mechanisms that are limiting? So
one of the reasons that we started doing a little bit of an investigation of this is that we wrote a proposal in which we actually suggested that we could manipulate the current that is produced by a solid oxide fuel cell, or that is consumed by a solid oxide electrolysis cell, at grid cycle frequencies. So
what do you mean by grid cycle, Jack?
We're just meaning 60 hertz.
Oh, okay.
Okay.
Yes.
So that we could engender some of the features that ancillary services require, like voltage support or frequency support.
Yeah.
Okay. And so this is one of the reasons why we started looking at this. We've never tried that idea before this. So that's one of the reasons why we didn't start looking at the limitations that might be associated with that. So.
Okay. Cool.
Yeah.
Cool.
Hopefully I didn't give away a really good idea.
Hopefully me not. Hopefully I didn't too.
Maybe I can work with you on that one.
Yeah, we should talk about it. I'd love to chat more. I really enjoyed your talk. Thank you.
Cool. Thank you.
Thank you, Kyle. Thank you very much. I've got another question here, Zach. Are you still, strong? Because I'm assuming we exhausted you, right?
No, I'm fine.
We are designing and installing small SMR. Do you see this question?
I don't see that necessarily.
Let me read it for you. We are designing and installing a small SMR for hydrogen refueling at gas station locations. Replacing carbon capture technology on these systems, but we are running into what to do with the CO2 once it's caught.
This is great. This is a very interesting concept. As I mentioned in the very beginning, probably the third slide, hydrogen is difficult to move around in society in comparison to current infrastructure fuels, right? And as a result, this idea of on-site production at a fueling station is, I think, a good idea. It may even be an idea that becomes ubiquitous in our zero emissions future. Again, because mainly hydrogen is difficult to move around, okay? It carries less energy per unit volume than methane does, about a third, okay? Of course, on a gravimetric basis, it's really good, but it's usually the volumetric basis that we care about in terrestrial applications. And so maybe renewable methane is what ends up moving around in our pipelines, in which case we don't have as many materials considerations or infrastructure challenges. And then at the site of the fueling station, we could use SMR. Okay, of renewable methane, right? Okay, so this is a very interesting thing. And then if you would sequester the CO2 or recapture it out of the air, or so, then you end up having still that cycle that you can engender that is sustainable. But you're asking a very specific question about when you're using natural gas, so you're using fossil and you would like to get rid of the CO2. One of the things that you could do in many locations is you could try to establish a CO2 purchase agreement with an entity that wants to use the CO2, like Coca-Cola. Typically, though, they already have well-established agreements at very low prices, and this is such a small amount that it might not, but maybe for their renewable future, they may think about agreeing to doing something like this, right? And then to using that in something, like their carbonation processes. There are other uses for CO2 that we have thought about, but it's quite difficult at the distributed scale to make these make a lot of sense. Okay, and a hydrogen fueling or a fueling station is quite a small scale of CO2 production. The most economic means of dealing with CO2 is already being used widely in enhanced oil recovery and injection into existing oil and gas fields. This is what people are doing the most today. So if you happen to have fueling stations that are on top of something like that, well, then you could actually start to sequester it that way. That's going to be few and far between, I think. But well, maybe that helps a little bit with regard to that.
And what about using ammonia for hydrogen transportation versus hydrogen gas or liquid? So ammonia is another big science question, right?
Yes, yeah, terrific. Ammonia is required for fertilizer. I think it will be a mass manufactured and a mass transported product forever, I think. And as a result, making ammonia from renewable hydrogen is very important just from its fertilizer properties. And yet we also have a very interesting fact that when ammonia is subjected to about 100 psi of pressure, very low pressure, it can carry more hydrogen per unit volume than liquid hydrogen. This makes it a very interesting carrier of hydrogen and maybe also a very interesting zero emissions fuel. We have had conversations with Maersk and with NYK, major shipping companies, and they are very interested in the use of ammonia as a vector for zero emissions. One of the reasons is they have ships already today that are transporting ammonia all around the world, and so they know how to handle it. They don't yet know how to handle hydrogen. So ammonia is going to be a very important commodity in itself and may become an important energy carrier, hydrogen energy carrier in the future. And so this is a very important topic. I appreciate the question. We have begun to do some research to also look at electrochemical means of producing ammonia that you could possibly even do at small scale and efficiently, which is kind of an interesting complement to the renewable hydrogen production, because ammonia production today using the Haber-Bosch process is only really efficient at these huge scales, okay? And so electrochemically, we think we can get down to smaller scale and be just as efficient. Anyways, so this is a very interesting research topic, yeah.
Well, thank you again, Jack, for your thorough and lucid answers that you provided to every question we had. I also would like to thank all the participants. I think they raised intriguing questions that
yes,
are
indeed.
to the core of this new hydrogen economy that we are all aspiring, industry, university, and citizens. So I leave it up to you to close it in case you want to say a few words. And I would like personally to thank you again for this informative and insightful engagement with us here at Midwest.
Well, thank you so much, Petros. I appreciate your invitation. I appreciate the work that you and so many colleagues are doing in this space and related spaces. It is really important to me that what we are doing today is required for us to really achieve a zero emissions future and to engender energy and environmental justice and equity. We have a chance, okay? We have a chance to do that if we are open to the panoply of technologies, solutions, and policies, okay, that are required to engender this. I've been disappointed in recent years that we have fighting amongst us. I'm disappointed that Elon Musk calls these fool cells and says it's foolish to invest in hydrogen. I know he's going to change his mind. I know he's going to change his mind because we've been studying batteries, fuel cells, electrolyzers, hydrogen energy storage. They provide different features. They provide different features. We need all of these technologies, and all of these are required for our zero emissions future. That diagram that we had in our science paper, I want to point to that again, because it included bioresources, nuclear, it included wind, solar, electrolysis, hydrogen, chemicals. It included batteries, includes all of these things to get to this zero emissions future. And I thank you for letting me preach to you a little bit on this topic, but also to share with you both my passion and some of the research that we have done to engender this zero emissions future. And the Midwest is going to have a lot to say with regard to this. I was really pleased to be invited to the Midwest Hydrogen Coalition to be able to speak there. I'm super pleased to be able to speak to you at the University of Illinois Urbana-Champaign and others that are in the Midwest. Thank you so much.
Thank you again. Thank you very much. Thank you. And that concludes our presentation and our event for today. Thank you very much. Thanks to every participant. Thank you.
Thank you.
Thank you, Jack.